Please let's get started. We're looking at one-dimensional WKB theory, so we want to solve the Schrodinger equation in one dimension, pretty simple equation with some energy E, so we're looking at energy I these days. If you imagine the potential has a scale which I call capital L, I've kind of sketched here what that means. We're interested in a situation in which the de Broglie wavelength of the wave function, which we call lambda, is much less than the scaling. In fact, that's the condition of validity for WKB theory, that lambda be much less than L. The lambda, of course, is related to the momentum by the de Broglie relation. It's 2 pi h bar divided by t. If I use the de Broglie relation, then one can say that the lambda is small if h bar is small. And frequently the WKB approximation is described by saying that it's valid if h bar is small. It isn't really dimensionally correct to say that. If you want to put it in dimensionally correct language, you should say that the wavelength is much less than the scaling of the potential. Nevertheless, the WKB expansion is, in a sense, a formal power series expansion in powers of h bar. Now, by looking at this, by the way, the momentum that comes from the de Broglie relation is now a function of position, because the wavelength of this wave actually changes as you move around. And we need to interpret what this momentum function is. That's something to pay attention to. And in the case, this leads, by looking at a picture like this leads to the WKB ansatz of the wave function, which is that it's a slowly varying amplitude times a rapidly varying phase. Slowly varying means varying in the scale length of the potential, as you see by this amplitude I've drawn here. And rapidly varying phase means that in a short change in x, the phase undergoes several oscillations. In fact, in a single wavelength, which is regarded as a short length here, the phase changes by, of course, by 2 pi. If you think of h bar as being small, the rapidly varying phase is achieved by the fact that since you've got this h bar in the denominator here, the small change in s produces a large change in the phase. In any case, by requiring the change in s be equal to 2 pi, when delta x equals lambda, at the end of the hour last time we derived this relation that said that s prime of x, the derivative of the function that appears in the phase, is equal to this momentum function p of x that comes from the de Broglie relation. Now pay attention to this function p of x, because it's being defined here in terms of the local de Broglie relation of the wavelength of the quantum wave. But it also has a classical interpretation, which is going to come out in a minute. So these two things will be connected together. This also, as I said, the derivative of s. All right, so I think that takes us up to where we were at the end of the hour last time. Now, this WKB ansatz, so the name of the next step is to use this WKB ansatz, in effect, plug it in the Schrodinger equation and get equations for both A and S, and then we've got the solution in this approximation. The WKB ansatz by itself is not a systematic expansion in powers of h bar. It's rather just something we wrote down by intuition by looking at a picture like this. However, we can put it into the form of a systematic expansion, which I think clarifies the structure of the theory in the following way. First of all, let me just rewrite the WKB ansatz by bringing the amplitude A up into the exponent. So I'll write it as e to the I over h bar times s of x plus the logarithm of a. That's no change, of course. But when we do this, you can notice that when L appears in the exponent, it's starting to look like a power series and expansions in powers of h bar. The first term goes as h bar to the -1, and the second term goes as h bar to the 0. And so what this suggests is that we replace this by a systematic expansion that looks like this. E to the I over h bar times the series, which I'll write up this way. So let's say W0 at lowest order plus h bar times W1 of x plus h bar squared times W2 of x plus ... like this. So if we replace the wave function psi by this expansion in the exponent, you can see the idea is that we're making a power series expansion of the logarithm of the wave function. In powers of h bar, where we're thinking of h bar as being small. Now, why don't we expand the wave function itself? If you're going to study the semi-classical limit, you think h bar is small, you'd want to expand psi in powers of h bar. The answer is that when h bar goes to 0, if you hold classical quantities fixed, psi does not approach a limit at all. Instead, it just starts oscillating more and more rapidly because the de Broglie wavelength gets shorter and shorter. So it's not suitable to expand psi in powers of h bar. Instead, we're going to expand the logarithm of psi, factoring out a 1 over h bar, which is what takes care of the rapid oscillations. So in any case, this is what we get, and it's a systematic expansion. Let me just call this entire exponent, let me just call it w of x, like this, in effect relating psi to its log w in this manner. So I'll copy it again here. Just say psi of x is equal to e to the I over h bar times w of x. This becomes a definition of w now. So the next step, what I want to do is to take this version of psi and plug it into the Schrodinger equation and get an equation for w. Oh, by the way, maybe before I do that, let's notice in comparing this series here, w0 is the same as s. So let's write that down. W0 of x is the same as s of x. It's just another notation for it. And w1 is equal to the logarithm of a, except I have to multiply by i's. So w1 of x is equal to, as you'll see, minus I times the logarithm of a. And then there's higher order corrections too, which were actually further refinements on the original WKB size. All right, so to get back to where it was just a moment ago, let's take this expression for psi and plug it into the Schrodinger equation. We have to evaluate the kinetic energy term, second derivative of psi. So let's start taking derivatives. Psi prime, you see, is equal to I over h bar times w prime multiplied times psi. First derivative. Taking the second derivative, psi double prime is equal to, first I differentiate the w, so I get I over h bar w double prime times psi. And then differentiating psi brings down another factor of I over h bar times w prime, so we get minus 1 over h bar squared times w prime squared times psi. And if it will allow me to do a bad thing, which is to use my eraser here, I'll just factor out the common factor of psi in both these terms and write it like that. All right, so that's just algebra. Now if I plug this psi double prime into the Schrodinger equation, since you now see psi double prime is proportional to psi, and the potential energy term is also, and the total energy are also both proportional to psi, when I make this substitution, the psi's cancel from all three terms. And so what's left over is this, and it's minus h bar squared over 2m times this coefficient in the round brackets. I'll reverse the order of the terms. Minus 1 over h bar squared, w prime squared, plus I over h bar times w double prime. And then add the other two terms, which is the potential energy V of x is equal to E. And this is what we get. And let me now just clean this up, multiply through by minus h bar squared over 2m. And what we get then is that 1 over 2m times w prime squared minus I h bar over 2m times w double prime plus v of x minus e, is equal to e. Like this. And I'll put a box around this because it's a useful intermediate step to look at. This is the Schrodinger equation, which has been transformed from psi into its logarithm. But in fact, there's no approximation at this point. It's exactly equivalent to the original Schrodinger equation. However, what I will do now is to substitute this expansion in for the w's here. So this becomes 1 over 2m, and then for w prime, it becomes w0 prime plus h bar times w1 prime plus dot dot dot, quantity squared. That's for the first term here. Then we get minus I h bar over 2m times w double prime, which is the same as w0 double prime plus h bar w1 double prime plus dot dot dot, plus potential energy V of x equals E. Well, now what we want to do is to take this series and to collect it order by order in powers of h bar. So h bar to the 0 power, which is the leading term, as you see, we just take the w0 prime here, which is squared. So the first term is 1 over 2m times w0 prime squared. And then the next term is already order h bar, so it doesn't contribute to h bar to the 0. And then there's the potential and the energy E, which don't depend on h bar, so this becomes plus V of x is equal to E. And let me back this off a little bit to the h bar equals 0 so you can see the equation better. So this is the lowest order equation we get. Now, at first order in h bar, we'll go to the first two orders in this. At first order in h bar, there's a cross term here by multiplying these two terms together because it's being squared. So I get 2w0 prime times h bar times w1 prime divided by 2m. So this gives me 1 over m times w0 prime times w1 prime. Over here, like I do get an order h bar term from the w0 double prime, so it becomes minus I over 2m times w0 double prime. And then b and e don't contribute at order h bar, so the whole thing is equal to 0. And this is the beginning of a hierarchy of equations. I'll stop there, but if you were motivated, you could go on to second order and create another equation. Observe the general structure of these equations. The first one is an equation for w0 alone. It doesn't involve it into higher order terms. And if you solve this for w0, then you can plug that into the second equation here and here, and then you get an effective equation for w1. And likewise, if you go to the next order, you plug in so you solve this one for w1. Then you go to the next order, you can plug w0 and w1 and get an equation for w2, and so on. It's a hierarchy that goes on this way, and you can solve it order by order. We're only going to be interested in the first two orders. Now, let's take these equations here in terms of w0 and w1, and let's put them back in terms of the amplitude and phase of the original WKB ansatz. So for the first equation, that's easy. It becomes 1 over 2m times s prime squared plus v of x equal to e. And for the second equation, let me do some algebra on that. First of all, the m's will cancel, as you see here. So the w0 prime becomes s prime. The w1 prime, since w1 is minus I log a, this becomes minus I times a prime divided by a. And then the second term is minus I times s double prime. And that whole thing is equal to 0, because w0 is s. So it's minus I s w prime, this is over 2. S double prime equals 0. And you change the two minus signs to a plus, we cancel the i's, so they go away. And this can be written now as a prime over a times s plus 1/2 s double prime equals 0. And since I'm sort of running out of room, let me carry it on over here. And if I take this equation, and let's multiply it times twice a squared, which cleans it up, then the first term becomes 2a prime times s, this should be s prime. And the second term becomes a squared s double prime equals 0. This, in turn, is an exact derivative on the left-hand side. In fact, it can be written as d dx of the quantity a squared times s prime equals to 0. And that's the most convenient way of writing the first-order equation after we've converted back into these s and a variables. So over here in this box, then, is the version of the equations that I want with the function s and the function a, which are the two functions, the amplitude and the phase, which occur in the WKB ansatz. All right. Now, I really started writing on the wrong board here this morning, so I'm afraid I have to cover this up. I will write out for you these two equations once again. And here they are. So the first equation over h bar to the 0 is this. It's 1 over 2m s prime squared plus v of x equals e. And then order h bar to the first equation is v dx h squared times s prime of x equals 0. That's pretty simple equations, actually. The first equation is actually a version of the so-called Hamilton-Jacobi equation, which has a long history in classical mechanics that goes way back before the invention of quantum mechanics, 1830s, 1840s. Second equation is sometimes called an amplitude transport equation, and that's what I'll call it just to give it a name. So we need to solve these two equations. All right. Now, we need to solve let's solve the Hamilton-Jacobi equation first. Obviously, the way to do that is this is S prime, not S12, S prime squared. Obviously, the way to do this is to solve algebraically for S prime. And if we do, we find that S prime of X is equal to plus or minus, just bringing the 2m across and taking the square root, plus and minus the square root of twice the mass times the energy E minus E of X, like this. Let's just take the plus sign on this for now, and we'll worry about the minus solution later on. I'll remind you from the previous board that we figured out that S prime of X was the momentum, which was the momentum determined by the local de Broglie wavelength. If we take that as this function, definition of this function P of X, what we now see is that we have a little additional information now as we see we have a formula for P of X. With that de Broglie wavelength, local de Broglie wavelength of the WKB wave function. What does it mean, however? Let's get an interpretation of it. In order to do that, let me take an example. Let's suppose we have a potential energy that looks like this. Still a one-dimensional problem. Let's suppose the potential is essentially 0 for large negative x, but then as we move in the region of positive x, it rises up, like going up to a mountain. And let's say it stays up forever, so there's no possibility of penetrating through this mountain. And let's suppose there's an energy E which looks like this. Now the energy E that I want to talk about is the energy that appears in the Hamilton-Jacobi equation. And actually that energy is the same as the energy eigenvalue in the original Schrodinger equation. That's where that came from. And but in a picture with the potential, it looks like this. Now, classically, a particle coming in from negative x would originally be a free particle because the potential is 0. This is the V of x curve here. But as it comes in, it starts to feel the potential and slows down and reaches, it comes to a standstill when the energy is, kinetic energy is 0, which is right here. This is the classical turning point, which I'll call xtp. And then, of course, it reverses and comes back. If I take some x value, some typical x value here like this, then you can see the particle passes this point x twice. Once going in the forward direction and once going in the backward direction. And the magnitude of the velocity, of course, is the same in both cases, but the sign is changed, going back and forth. Now, on the same scale, allow me to make a phase space of the classical phase space, the position momentum phase space. And let me bring this x turning point down here also to the lower graph, like this. So this is still xtp. The orbit in phase space at large negative x is a straight line at a constant momentum because the particle is really free. So the momentum is constant and it just keeps moving forward in x. However, when it starts to get to where the potential is active, it slows down, so the momentum goes down like this, and then it goes right through momentum equals 0 at the turning point, and then turns around, like I sketched this well, and comes back out like this. So the orbit in phase space is a picture that looks like this. It's kind of a loop thing. This is really a scattering problem. It's a one-dimensional scattering problem off of an impenetrable barrier. Likewise, if I take this typical x value here and bring this dotted line down like this, and again, here's some typical x value, what you see once again is that the velocity, the particle passes this x point twice, once going in when the momentum is positive, and once going back out when the momentum is negative, like this. Now, this curve in phase space, what is the equation of this curve? The answer is it's just given by conservation of energy. If we write down the total energy of the system, which is p squared over 2m plus v of x, this is now the classical energy. Instead of equal to the total energy, which of course is conserved, then you get an equation for a curve in the xp plane, and it has to be the orbit. The orbit is just the plot of a curve, which you get by setting the classical Hamiltonian equal to the energy. And in particular, this allows us to solve for the momentum values that correspond to a given x position. And that momentum, just solve this equation for p, and that momentum gives us p is a function of position, as you see, and it's the square root of twice the mass times the energy minus v of x from the Hamiltonian. Well, that agrees with the same p of x that came out of solving the Hamilton-Jacobi equation from the WKB approximation. So the local momentum connected with the local de Broglie wavelength in the WKB wave function is exactly the same as the momentum of a classical particle, which is moving on the given potential with two signs, plus and minus. So that's the interpretation of this function p of x. And you can see now right away that the de Broglie wavelength is going to be shorter where the momentum is higher, where the velocity is higher, and it will be longer as the particle slows down. I didn't exactly sketch that very well on this diagram, but it would mean that as we rise up in the potential, so the velocity decreases, this wavelength is going to get longer down here, this lambda. All right. Now, so that's the interpretation of this function p of x, which is also s prime of x. And so now the solution for s of x is easy. It's just an integral with an upper limit of x of p of x prime dx prime. Which, to be a little more explicit, is with an upper limit of x of the square root twice the mass energy minus v of x prime times dx prime, like this. What about the lower limit of this integral? The lower limit of the integral is nothing but a constant of integration of the Hamilton-Jacobi equation. You can set it equal to anything you want because it's a constant of integration. We just call it x0. You can see that if you change x0 to something else, x0 prime, all it's going to do is just add a constant to x. And since s is the phase of the wave function, let me write the WKB ansatz down again so that you have it here on this board. If I change the phase s by a constant, actually the phase is s over h bar, but if I change s by a constant, you can see it amounts to just changing the phase of the wave function. So this lower limit x is related to the phase convention for the solution. And right now, let's worry about phase conventions later, so we can set this x0 to anything that's convenient. Anyway, that's just the meaning of that lower limit. There's also a geometrical meaning now. If I take x0, let's say over here, just to choose some value for it, then s of x is the integral of this p function between x0 and x, which is to say this is area here. So the area here under the classical curve is the same thing as this function s of x. One might say that as the classical particle moves along, you can visualize that as it carries a little integrator with it, and it integrates p dx. And as it does so, what is accumulating is this function s of x, which is divided by h bar, is the phase of the quantum wave function. So you can imagine that it's also creating oscillations going up and down as it moves along. It's a way of thinking about the solution. Now, I'd like to shift attention now to the quantum interpretation, but with this WKB ansatz, in particular to examine the probability density and probability current. This is only a one-dimensional problem, so the current is just a scalar element vector of one component. But if we use the definitions we've talked about before, the probability density is the square of psi, and the probability current, which I'll call J, I'll remind you is the real part of psi star, and then you have a velocity operator, which is minus IH bar over the mass m acting on psi. This is the definitions we gave. Oh, excuse me, it's minus h bar over m times the derivative, d dx acting on psi. This would have been a gradient in 3 dimensions, but since this is a 1D problem, these are the definitions we have. Now, if I take the WKB ansatz, this is only an approximation, remember, but in this approximation, let's take this and plug it in here and see what we get. Well, you can see right away that rho is just equal to the square of the amplitude. That's assuming that S is real, but S is real, as you see up here in these pictures that I've sketched. So that's easy. It's just a squared is just the square of the wave function. What about j? Well, that's equal to the real part of, here, I'll fill it out for you. Psi star is equal to the amplitude times e to the minus IS over h bar. And then we have minus IH bar over m, which is a constant. And then we have d dx applied to psi, which is way up there. There's two terms. One comes from differentiating a, and the other one from the exponent. So one term gives us an a prime, and the next term gives us a plus I times a times s prime over h bar, and this is all multiplied times e to the I s over h bar, and I close all of that. So this is just doing the algebra of calculating j. Now, this term I here times the amplitude a, as you can see, is purely imaginary. And this term here times that second term that has an I in it, it's now got a minus I times a plus I, so this is purely real. Well, the result is this a prime term goes away because we're taking the real part. And what's left over is that this turns into an a squared, which takes care of that a and that a there. The phase here and here, two phases cancel out because they're complex conjugates. Minus I times plus I cancel. There's a 1 over m. The h bars cancel. So what's left over is just s prime divided by m. Okay? However, we decided that s prime was the same thing as this momentum function p of x, which we have an interpretation for up here. And this is divided by m. Let's call p of x, let's call it a velocity. Let's call it v of x. So it's a logical definition here. P is the momentum of the particle. I can't reach it. I'll just say v of x is p of x over m. So this is just the velocity of the particle at a given x position. Really one of the two velocities because there's plus and minus for the particle going in both directions. Let's take this to be the positive velocity. And so to summarize, then we get j rho is equal to a squared, and we get j is equal to a squared times the velocity v, which is a function of x, like this. Okay, so in the WKB approximation, these are the quantum, density, and current. Now these have to satisfy a continuity equation. This is the continuity equation, which we talked about last hour, I believe. Except in one dimension, instead of a divergence, it's just going to be an ordinary derivative. So, well, it's going to be partial derivative, partial to j with respect to x equals 0. So this is the one-dimensional continuity equation. However, nothing here depends on time. Everything's rho, for example, is just a function of position. That's because the original Schrodinger equation they're looking at is the time-independent Schrodinger equation. So we're really interested in stationary solutions. So this term goes away, and so the continuity equation just turns into the derivative of j. In fact, we might as well call it an ordinary derivative since there is no time derivative anymore. And so the continuity equation reduces to just dj dx is equal to 0. However, j is a squared times v, so this becomes d dx of a squared times v of x is equal to 0. And apart from the factor of 1 over m, you'll see, lo and behold, somewhere here, yes, up here, that's the amplitude transport equation. So the meaning of the amplitude transport equation is conservation of probability. It's the continuity equation for that. All right. Given that fact, so now we have an interpretation for both of these equations. And also for the function. Well, we have an interpretation for S in terms of the classical mechanics. What about an interpretation for A? Let me address that question next. Say a classical interpretation. It works like this. To be specific, let's take the case of an oscillator. Suppose I have an oscillator like this, and in phase space, this is the orbit, so the particle is going around and around in circles like this. The topological circle. For a harmonic oscillator, this is an ellipse, but for other oscillators, nonlinear oscillators, it will be deformed and look like an egg or something, but topologically it's a circle. Now, let's take some small interval dx like this. Oh, and by the way, let's let capital T here equal the period of the oscillator, the amount of time it takes for the classical particle to go around. And let's define I'll call it a classical probability density, which is a function of x. And it's defined this way. We'll say the classical probability at x times dx, which is a small interval. This, of course, is the probability of finding the particle in this small interval. Let's declare that this is equal to the amount of time dt, which the particle spends in this small interval, divided by the total period. It's just the fraction of time that the particle spends in that small interval. Then if we do this, this clearly is normalized to 1 around the oscillator. One slight thing to change, however, is a question of the interpretation of dt. The total time the particle spends in this interval is a dt from 1 above and a dt from 1 below. So this dt really stands for the sum of those two small time intervals. It might be preferable to let dt stand for the time that it takes the particle to cross this small interval on just one of these two crossings. And if we do that, we want to put a factor of 2 here to double back. And then with that new interpretation of dt, this becomes the classical expression. Now, we can then solve for rho classical of x explicitly. It becomes 2 divided by the total period times dt divided by dx, which is equal to 2 over the period times 1 over the velocity. Now, why is that interesting? It's because it agrees with the solution of the amplitude transport equation. Here it is. Here's the amplitude transport equation. It really came from the continuity equation. Since ddx of this thing is equal to 0, it says that a squared times the velocity d of x is equal to a constant. However, a squared is a quantum probability. And so plugging this in, you see the quantum probability rho of x is equal to a constant divided by the velocity v of x. And so it agrees with this classical calculation. This quantum probability density in the semi-classical interpretation is the fraction of time which a particle spends, well, times dx is the fraction of time the particle spends in that interval dx. Here it's explicitly normalized to unity for the case of an oscillator. If we had a scattering problem, which is the kind of thing I have in the upper board here, I don't even need to draw it again, where the orbit goes out to infinity, then in that case it's not possible to normalize the classical probability distribution because the period, there is no period, t goes to infinity. But it's still possible to talk about a classical density, which is just now not normalized. We can just, in this case, we can just say the classical density is equal to some constant divided by the velocity v of x. And this is, in fact, precisely what we get from the solution of the amplitude transport equation. So this then gives an interpretation of a classical interpretation of the amplitude A in terms of particle densities. By the way, there's a consequence of this result. This now becomes the same thing as the quantum rho, you see. Classical rho and quantum rho are the same. The consequence of this result is that when the velocity gets low, the density gets high. In the case of this oscillator here, if I plot, again, this now has 2 turning points. Let me plot rho classical as a function of x for this oscillator. It looks like this. It actually goes to infinity as the velocity goes to 0 at the turning points. You'll find classically this is still normalizable. The Aristotelian area of the curve is finite, but nevertheless there's a divergence in the classical density. Here's another way of thinking about this classical density. Let's imagine that we populate this orbit with classical particles in such a way that individual particles are separated by the same amount of elapsed time. You see, each particle is following an orbit. It's the same orbit, and they're just displaced. They're just in different places along the orbit, so they're all moving around the orbit at the same time. When I say they're displaced by a certain amount a fixed amount of time, there's some delta t here, and the idea is that after delta t, each particle moves into the position of the next particle. If you think of delta t getting smaller and smaller, so there's a higher and higher density of particles, then the particles are all moving, but they're moving in such a way that the density of particles that they create is constant in time. So one can say that it's a an ensemble of classical particles, which is whose density is stationary in time. And that's what's appearing in the solution of the eigenvalue equation stationary state problem in quantum mechanics. All right. The particles pile up here at the turning points because you see they don't pile up in the orbit in phase space, but they pile up in the density in X space because they're getting projected down like this, and there's the slope of this curve is coming down. That's the reason for that. Okay. So most of what I've been saying here has to do with classical interpretations of the solutions of these two equations, the Hamilton-Jacobi and amplitude transport equation. It's actually easy to solve the equations. It's just a matter of interpreting them and knowing what they mean. Right. Right. Now, conveniently have these two equations still here. So to summarize the solution then, we've got S prime of x is equal to P of x is equal to the square root of 2m times e minus v of x. So S of x is the integral of that. Upper limit x of P of x prime dx prime, like this with some lower limit. And as far as the amplitude transport equation is concerned, it says that a squared is 1 over s primes, 1 over the momentum. So a of x is equal to 1 over the square root of the momentum p of x times a constant here, like this. And that's the solution for the amplitude transport equation. If I factor a mass out, a square root of mass out of the constant, it converts this momentum into a velocity. It takes it back to these classical densities that I'm talking about up here. This constant that appears here is just the constant of integration of the amplitude transport equation, and you can see that it also is just related to the normalization of the quantum wave function, which again you seem to have lost it. In the WKB ansatz is that it's the amplitude times the phase, and so obviously a constant multiplying a is just an overall multiplicative constant on the side. So we can, and likewise I said x0 is related to the phase of the wave function. We can worry about normalization and phase later, so these two constants we can set to something which is convenient at a later point. All right, now then, this means that if I let me go back to this case of the scattering problem where the potential rises like this. Here's an energy E. Here's the turning point. Sketch it again. Here's the turning point. Here's x, p. Here's the phase space orbit coming down like this, going in and out. All right. So this is the solution for A and S here. There's a couple of things that I need to, a couple of minor points I need to pay attention to. One is that in solving the amplitude transport equation, there were really two solutions for S prime having to do with a plus or minus on the square root. And I just took one of the two solutions when writing these equations down. But the other one is in there, and it just has the opposite sign. So S is equal to plus or minus the integral effect of the two solutions. The result is we actually get two solutions of the WKB equation. So if I write psi of x out explicitly, there's an amplitude for about one of them is 1 over the square root of p of x. I'll set just 1 here for this constant. And this is multiplied times e to the I over h bar s of x. But there's another solution, which is 1 over the square root of p of x times e to the minus I over h bar s of x. There's really two linearly independent solutions. This, of course, is what we'd expect because the Schrodinger equation is second order and has two linearly independent solutions. So the general solution is going to be a linear combination of these two. Now, in one of these solutions, the function s is increasing as I move to the right because it's the area under the curve. So the phase is increasing as we move to the right, and that corresponds to a wave which is traveling in forward direction, just like in the positive momentum. Whereas the second term, S the phase is decreasing as x increases, which means there's a wave here which is moving in the other direction. And so the linear combination is a linear combination of forward and backward going waves, which correspond to the two particles which are crossing a given x position, like this. If you think of this just in terms of one particle, you don't see it because you see a positive velocity at one point and later a negative velocity. But think about this curve as being populated by a whole ensemble of classical particles. And then there's always one particle above and one particle below, and their phases are increasing in opposite directions. Here's something I meant to say a moment ago. The WKB theory expresses, in an approximation, expresses the solution of the quantum problem in classical terms. But physical interpretation of quantum mechanics, of course, is very different from classical mechanics. And in particular, quantum mechanics is statistical fundamentally, and classical mechanics is not. So how does this very different physical interpretation come about in this approximation? It's one of the questions to ask when you start this business. And we can already see part of the answer to that is that the statistical aspects of the quantum solution is contained in this classical ensemble of particles that are orbiting around and around this orbit. Or in the case of an oscillator, there's an infinite number of them coming in, scattering, and going back out again. It's not a single classical particle, but a whole ensemble of them. They all, however, have the same energy because they all lie in the same orbit of fixed energy. All right. In any case, these two solutions, one is moving to the right, one is moving to the left. So let me give this a coefficient I'll call CR, and this one a coefficient I'll call CL, where R and L just stand for right and left going waves. And if we have this, then this is the solution. This is the WKB solution that we get. All right. Now, there's another point that I've been omitting up to this point, which is that these solutions that I've worked out here actually only apply in the classically allowed region. In this diagram here, for example, the classically allowed region, CAR, let's call it, is the region which is to the left of the turning point. This is where the actual particles are moving. But there's also a classically forbidden region that's called the CFR, which is over to the other side, and this is where there are no classical particles. There may not be any classical particles over there, but there are solutions of the Hamilton-Jacobian amplitude transport equation. In the classically allowed region, the energy is greater than the potential energy. That's really the definition of that. Whereas the classically forbidden region is one where the energy is less than the potential energy. That means that in the classically forbidden region, you would say the kinetic energy is negative, which would mean the momentum is imaginary. That doesn't have any meaning in classical mechanics, but it does have meaning for solving these quantum equations. And so in the classically forbidden region, what's going to happen is this quantity here is negative. So this little box here, let me just say that this box that I've got here applied in the classically allowed region. And let's write down some things that would apply in the classically forbidden region. Let's just do it this way. So in the classically forbidden region, let's define this. Let's write P of x. P of x now has to be purely imaginary. Let's write it as I times the square root of 2m times d of x minus e. This is just a way of defining one of the two solutions, plus and minus, for the function P of x. And let's define an integral called k of x, which is an integral with some upper limit, and it would be the integral of the absolute value of P of x prime dx prime, which is the same thing as an integral with an upper limit x and some lower limit of the square root of twice the mass times potential d of x minus e dx prime minus e dx prime. Okay? And if we do this, then s of x, which is s of x is equal to I s of x is equal to minus k of x. So over here in the classically, so this solution I wrote down at the bottom of this board is for the classically allowed region. In the classically forbidden region, we can say this, that psi of x is going to be a linear combination of a term which is 1 over the square root, and I'll write its absolute value of the momentum to make it real. And then we get e to the k of x over h bar. And then another solution is 1 over the square root of the absolute value of p of x times e to the minus k of x over h bar in the classically forbidden region. There again are two linearly independent solutions. K is increasing with x. And so the term that has e to the k of x over h bar is a term which is diverging exponentially as you move in the positive x direction. So let's call this CG, where G stands for growing. With a minus sign, it's a solution which is decaying exponentially as you move to the right. So let's call this damping solution CD, growing and damping solutions as you move to the right. And the result of this is that we have now the two solutions here in the classically allowed and classically forbidden regions. All right, now to proceed with this, let's take the case as I've sketched it here, exactly as already sketched, in which the classically allowed region is to the left of the turning point, and the classically forbidden region is to the right. We can also call these regions 1 and 2 if you like. That might be useful. And let's do it this way. In the classically allowed region 1, which I'll put over here in this box, let's make the lower limit of integration. Let's make it the turning point, which I'll call, instead of xtp, let me call it xr, where r stands for right. It means the right turning point. So let's call it xr as the right turning point. And let's integrate s from, as I mentioned, any lower limit can be chosen. It's equivalent to a phase convention for the wave function. So let's just make it the turning point. It's the obvious place to choose. Anyway, then that gives us a definite definition for s of x. And likewise, in the classically forbidden region, let's take the lower limit here to be xr. That means that both k and capital S vanish exactly at the turning point. So those are definite conventions for that. All right. So then now what we have then is a definite functions here with unknown coefficients. Actually, 4 definite functions and 4 unknown coefficients when applying in 2 different regions. The Schrödinger equation is second order in time, in space, excuse me, second order in space. So it has 2 linearly independent solutions. And so the general solution of the Schrödinger equation can only involve 2 arbitrary constants and not 4. So there has to be a connection between these 4 constants, the right and the left, and the growing and the damping constants. They, of course, apply in different regions of space. So what we need is some way of connecting together the solution on the left side with the solution on the right side. These are called connection rules. Now, it's not possible to extend the classically allowed solution right up to the turning point, and the classically forbidden region right up to the turning point, and then matching them there in order to get the connection rules connecting the coefficients. The reason for that is that neither one of these solutions is valid in the immediate neighborhood of the turning point. In fact, it can be shown that there is some small region around the turning point where both these solutions are invalid. Why is that so? They're invalid there because the momentum, the velocity and the momentum are going to 0 at the turning point. But remember that the du Bois wavelength is 2 pi h bar divided by the momentum p, so this actually goes to infinity at the turning point. And the result is that the condition of validity in WKB, which is that the wavelength should be small compared to the scaling of the potential, breaks down. So if you look at this more carefully, you can actually estimate what size of the region around here the formulas are not valid. I won't go into that, but let's just say that because of this small region around the turning point where neither one of these solutions is valid, it's not possible to find the connection coefficients by just bringing them both up to the turning point. It'd be nice if you could, but it doesn't work out like that. So instead, what do? What we need is, in fact, is yet a third solution on top of those two. A third solution which is valid in the immediate neighborhood of the turning point. And this is done like this. Is, if I sketch my potential again, V of x, let's take this case here. Here's our energy E. Here's the turning point right here like this. I'm calling XR now. Let's approximate the potential by a straight line in the neighborhood of the turning point. So let's say here that V of x is approximately equal to V of x at the turning point XR plus x minus XR times V prime of XR. And if we plug that into the Schrodinger equation, it then becomes minus h bar squared over 2n times psi double prime plus this thing, V of x, so it's V of XR. Just copy it, x minus XR times V prime of XR times psi equals E psi. Now, V of XR, however, is equal to the energy E, because that's the definition of the turning point. That's where the energy is equal to the potential. So this term, V of XR, cancels the E term on the other side. And the result is that we get an equation which now just has this linear term. This, of course, V prime of XR is a constant here. Just has this linear term multiplying psi. The right-hand side is 0. This equation can be cleaned up and put into a standard form if we do a change of variables. Let's write x equals xr plus a constant a times z. So that z is a new variable, a is a constant here, z is a new variable, which is going to vanish exactly at the turning point, and it'll be negative on the left side, and it'll be positive on the right side, and otherwise it's just x scaled by a certain factor a. So we do a linear transformation of this resulting equation. Now we choose the constant a in order to clean up the equation and get rid of all the constants that are in here. And if you do this, you'll find that the nicest place for a is this. It's h bar squared, where is it here, over 2m times v prime evaluated at the turning point to the 1/3 power. And if you make that choice, then the Schrodinger equation becomes this. It becomes v squared psi dz squared minus z times psi is equal to 0. And that state's been cleaned up and all the physical constants disappear. This is one of the standard equations of mathematical physics. You can read about it in books like Memowitz and Stegun. And it has two solutions, psi of z. One is called the Airy function, ai of z, and the other is called the Airy function, bi of z. And the general solution is a linear combination of these two with coefficients I'll call Ca and Cb. Now, you can look in the books on special functions and get all the properties of the area and Airy functions. But in order to understand what you're reading from a physical standpoint, it helps to have a physical model to understand the results. The way that I've derived the area, this is the area equation, is by using an approximation to the potential, a straight line approximation. Of course, it's possible the potential really is a straight line everywhere, not just at the turning point. It could be like this. For example, if we had a particle in the gravitational field, then V of x, let's call it, would be equal to mgx. It would be strictly linear in the position. And so the area and Airy functions are the approximate solutions of the WKB approximation in the neighborhood of the turning point of an arbitrary potential. But they're also the exact solutions for a particle in a uniform gravitational field, or for that matter, a charged particle in a uniform electric field, which is the same story, because it's linear in x. So thinking about the physics of a particle, the quantum mechanics of a particle in a uniform electric or gravitational field helps us to understand the mathematical properties of the area and Airy functions. And that's where I'll pick up next time.
So is that I of z or AI of z?
It's AI is the name of the function. It's a two-letter name.
The I, the
VI is it's named after the British astronomer Airy, who lived in the 19th century. And there was nobody named Barry. There is nobody named B-I-R-Y, but there is a Barry, but it's not spelled that way. For those of you who came in late, this first homework got this thing rated in brackets. I'll reverse the order of the terms. Minus 1 over h bar squared, w prime squared, plus I over h bar times w double prime, and then add the other two terms, which is the potential energy V of x is equal to E, and this is what we get. And let me now just clean this up, multiply through by minus h bar squared over 2m, and what we get then is that 1 over 2m times w prime squared minus I h bar over 2m times w double prime plus v of x minus E, is equal to E. Like this. And I'll put a box around this because it's a useful intermediate step to look at. This is the Schrodinger equation, which has been transformed from psi into its logarithm. But in fact, there's no approximation at this point. It's exactly equivalent to the original Schrodinger equation. However, what I will do now is to substitute this expansion in for the w's here. So this becomes 1 over 2m, and then for w prime it becomes w0 prime plus h bar times w1 prime plus dot 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 quantity squared. That's for the first term here. Then we get minus I h bar over 2m times w double prime, which is the same as w0 double prime plus h bar w1 double prime plus dot dot dot, plus potential energy V of x equals E. And now what we want to do is to take this series and to collect it order by order in powers of h bar. Which is regarded as a short ring here, the phase changes by, of course, by 2 pi. If you think of h bar as being small, the rapidly varying phase is achieved by the fact that since you've got this h bar in the denominator here, the small change in s produces a large change in the phase. In any case, by requiring that the change in s be equal to 2 pi, when delta x equals lambda, at the end of the hour last time we derived this relation that said that s prime of x, the derivative of the function that appears in the phase, is equal to this momentum function p of x that comes from the de Broglie relation. Now pay attention to this function p of x because it's being defined here in terms of the local de Broglie relation of the wavelength of the quantum wave. But it also has a classical interpretation which is going to come out in a minute. So these two things will be connected together. This also, as I said, the derivative of s. All right, so I think that takes us up to where we were at the end of the hour last time. Now, this WKB ansatz, so I mean, the name of the next step is to use this WKB ansatz, in effect, plug it in the Schrodinger equation and get equations for both A and S, and then we've got the solution in this approximation. The WKB ansatz by itself is not a systematic expansion in powers of h bar. It's rather just something we wrote down by intuition by looking at a picture like this. However, we can put it into the form of a systematic expansion, which I think clarifies the structure of the theory in the following way. First of all, let me just rewrite the WKB ansatz by bringing the amplitude A up into the exponent. So I'll write it as e to the I over h bar times s of x plus the logarithm of A. That's no change, of course. But when we do this, you can notice that when L appears in the exponent, it's starting to look like a power series, and the expansions in it. Oh, by the way, maybe before I do that, let's notice in comparing this series here, the W0 is the same as S. So let's write that down. W0 of x is the same as S of x. It's just another notation for it. And W1 is equal to the logarithm of A, except I have to multiply by i's. So W1 of x is equal to, as you'll see, minus I times the logarithm of A. And then there's higher order corrections too, which were actually further refinements on the original WKB ansatz. All right, so to get back to where it was just a moment ago, let's take this expression for psi and plug it into the Schrodinger equation. we have to evaluate the kinetic energy term, second derivative of psi. So let's start taking derivatives. Psi prime, you see, is equal to I over h bar times w prime multiplied times psi. First derivative. Taking the second derivative, psi double prime is equal to, first I differentiate the w, so I get I over h bar w double prime times psi. And then differentiating psi brings down another factor of I over h bar times w prime, so we get minus 1 over h bar squared times w prime squared times psi. And if it will allow me to do a bad thing, which is to use my eraser here, I'll just factor out the common factor of psi in both these terms and write it like that. All right, so that's just algebra. Now, if I plug this psi double prime into the Schrodinger equation, since you now see psi double prime is proportional to psi, and the potential energy term is also, and the total energy are also both proportional to psi, when I make this substitution, the psi's cancel from all three terms. And so what's left over is this, and it's minus h bar squared over 2m times this coefficient in the round in powers of h bar. The first term goes as h bar to the minus 1, and the second term goes as h bar to the 0. And so what this suggests is that we replace this by a systematic expansion that looks like this, e to the I over h bar times the series, which I'll write up this way. So let's say w0 at lowest order plus h bar times w1 of x plus h bar squared times w2 of x plus dot 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 like this. So if we replace the wave function psi by this expansion in the exponent, you can see the idea is that we're making the power series expansion of the logarithm of the wave function in powers of h bar, where we're thinking of h bar as being small. Now, why don't we expand the wave function itself? If you're going to study the semi-classical limit, you think h bar is small, you want to expand psi in powers of h bar. The answer is that when h bar goes to 0, if you hold classical quantities fixed, psi does not approach a limit at all. Instead, it just starts oscillating more and more rapidly because the Broglie wavelength gets shorter and shorter. So it's not suitable to expand psi in powers of h bar. But instead, we're going to expand the logarithm of psi, factoring out 1 over h bar, which is what takes care of the rapid oscillations. So in any case, this is what we get, and it's a systematic expansion. Let me just call this entire exponent, let me just call it w of x, like this, in effect relating psi to its log w in this manner. So I'll copy it again here. Just say psi of x is equal to e to the I over h bar times w of x. This becomes a definition of w now. So the next step, what I want to do is to take this version of psi and plug it into the Schrodinger equation and get an equation for w. We're looking at, let's get started. We're looking at one-dimensional WKB theory, so we want to solve the Schrodinger equation in one dimension. Pretty simple equation with some energy E, so we're looking at energy I these days. If you imagine the potential has a scale which I call capital L, I've kind of sketched here what that means. We're interested in a situation in which the de Broglie wavelength of the wave function, which we call lambda, is much less than the scaling. In fact, that's the condition of validity for WKB theory, is that lambda be much less than L. The lambda, of course, is related to the momentum by the de Broglie relation. It's 2 pi h bar divided by t. If I use the de Broglie relation, then one can say that the lambda is small if h bar is small. And frequently the WKB approximation is described by saying that it's valid if h bar is small. It isn't really dimensionally correct to say that. If you want to put it in dimensionally correct language, you should say that the wavelength is much less than the scaling of the potential. Nevertheless, the WKB expansion is, in a sense, a formal power series expansion in powers of h bar. Now, by looking at this, by the way, the momentum that comes from the de Broglie relation is now a function of position because the wavelength of this wave actually changes as you move around. And we need to interpret what this momentum function is. That's something to pay attention to. In any case, this leads, by looking at a picture like this leads to the WKB ansatz of the wave function, which is that it's a slowly varying amplitude times a rapidly varying phase. Slowly varying means varying in the scale length of the potential, as you see by this amplitude I've drawn here. And rapidly varying phase means that in a short change in x, the phase undergoes several oscillations. In fact, in a single wave